Okay, now we're in section 16.5. We're going to talk about divergence and curl, which are two operators, in fact, that you can use on a vector field. We're going to start with the curl. Suppose you have a vector field f. We're going to assume just for the for curl that we're talking about a vector field in R3. We define the curl this way. So if f is given in component form, in this form, pi plus qj plus rk, then the curl is also a vector field that we obtain from f, and it's given in this form. So you notice that there's a difference of partial derivatives that occur in the components for I, j, and k here, but this is in fact a vector field because it's got I, j, and k components. This formula, notice I have given you no motivation for why we would define a formula. This seems like a bizarre way to define it. We're going to come up with an easier way to remember this using a determinant instead. But before we do that, we need to talk about something called the del operator. So the del notation we've been using for gradients so far. If you see del f like this, it means the gradient of f. But this little symbol is actually really useful for notational purposes, starting in this section. And you see this thing all over the place in vector calculus and in areas of the sciences that use vector calculus. So what is the del operator? Well, we think of the del operator as a vector. And in this case, we're thinking of it as a vector in R, or in with three components. It can be a vector with two components, but in all of the applications we're going to see here, it's going to have three. And it's not a vector in the traditional sense. The values that I'm seeing here in my components are not numbers. They're not scalars of any kind. They're differential operators. So this is an operator which takes the partial derivative of something with respect to x, and then here with respect to y, and here with z. So by themselves, this doesn't represent anything useful. You have to apply this del operator to something. So thinking of it in the context of the gradient, if I have del f, if I think of the del operator as a vector, and if I think of f as a scalar field, which is what a multivariable function is. Remember back in chapter 14 when we introduced the gradient, we took gradients of functions of the form f of xy or f of xyz. Those are scalar fields. If I think of this like scalar multiplication, a vector here times a scalar here, then I can write this in this form. So del f is equal to this vector with these differential operators times a scalar, and then we know how to multiply vectors by scalars. We bring the f into each component. Well, even though this has the appearance of multiplication, it's not actually multiplication that's occurring. This is saying the partial derivative with respect to x of the function f, and then again with respect to y, and then with respect to z. So what we're doing is this is what we call an abuse of notation. This notation that we use to apply a differential operator to a function looks like multiplication, but it's technically not. However, because it looks like multiplication, we use concepts like scalar multiplication as the notation for concepts like this. So that's the gradient. That's something we've already discussed. But this idea of treating del as a vector and then performing vector operations on it with functions and vector fields and scalar fields, it allows us to make more concise notation of important things like curl and then later divergence. So we can think of the curl of a vector field f, this vector field up here, as a cross product of the del operator with our vector field. Now this makes sense because a vector field is in itself a vector where the components are functions of x, y, and z. So you take cross products of vectors with other vectors, which gives meaning to this. Now using the determinant notation for a cross product, I could think of it as this determinant. The determinant, the top row is my I, j, and k unit vectors. Del comes first in this cross product, so here's where my del vector shows up as the second row. And then F, my vector field, has component functions P, Q, and R, so that's going to be the third row. Now, if you think about it, if you were to take the determinant, this 3 by 3 determinant, and expand along this first row, you're going to have I times the partial derivative with respect to y of the function r minus the partial derivative with respect to z of the function q. But that's the very first term in this definition of the curl up here. And then these other two terms, of course, are going to come from continuing to expand that determinant. So it's a lot easier to remember this formula in this form, del cross f. So let's do an example where we want to evaluate the curl of a vector field. And here's our vector field, sine of yzi plus sine of xzj plus sine of xyk. Okay, so what I'm looking for, the curl of f is defined to be del cross f. And I want to point something out. I haven't been super consistent with my notation in these videos, and that's me just forgetting. But when I type, when I'm typing, I'm going to use bold for vectors and vector fields. Since I can't really bold when I'm handwriting, I'm going to use the arrow notation. This is equal to I, j, k, and then I have partial derivative with respect to x, then y, then z, and then I have my component functions, sine of yz, sine of xz, sine of xy. Okay? So, starting with my I component, I need the partial derivative of this function with respect to y, which is going to equal, if it's with respect to y, x is like the constant here, so it's going to come out, x times cosine of xy minus the partial derivative of sine of xz with respect to z. And so, again, the x is going to be treated like the constant here. It's going to come out as minus x cosine of xz, and there's my I component there. Minus, now I want to point something out up here. If you look at the definition of curl that we gave initially, you don't see a minus here, you see a plus. And the reason for that is because they're simplifying. If you were to evaluate this determinant for your j component, it's minus the partial derivative of r with respect to x first. But notice that shows up second in this difference. That's because they use the minus that would have been here to reverse the order of differentiation. So I'm actually going to do the same thing. I know that the minus is going to switch the order up. And so I'm going to be doing the partial derivative of sine of yz with respect to z first. That's going to give me y cosine of yz minus, then I need the partial of sine of xy with respect to x. That's going to be minus y cosine of xy. There's my j component. Now for my k component, I use this cofactor right here. So it's going to be the partial with respect to x of this guy. That's going to look like z cosine of xz minus this partial right here, so that's going to be z cosine of yz. Okay? And that's it. That's my curl. Notice it's a vector field. It's got an I, j, k component, and it's got these component functions here. All right? I'm going to scooch down here a little bit. Let's start talking about some theorems and some ideas that the curl finds its way into. So the first theorem says that if a function f is a function of three variables, and if it has continuous second-order partial derivatives, then the curl of the gradient of f is equal to the zero vector. Okay? Said a little bit differently, remember, if a function is conservative, then it's the gradient of some potential function. So we could also say this right here, because this is the gradient of a function, this is a conservative vector field. In other words, the curl of any conservative vector field is always the zero vector. that's useful because that gives us a criteria for ruling out a vector field, ruling out whether or not a vector field is conservative. So let's start by proving this theorem. It's fairly simple to prove, just comes straight from the definition of the curl. So if we wanted to take the curl of the gradients of some function f, that's del cross del f. Okay, so the first two rows in my determinant look as they do here. Remember, if I'm taking the gradient of f, then the components of that gradient are going to be the partial derivatives with respect to x, y, and z of our function f. Now, once we take this determinant, once we evaluate it, these are the terms that are going to show up. Notice I already have partial derivatives here, and then I'm differentiating them again with respect to different variables. So I'm going to have differences of second partial derivatives down here. But if you look carefully at the terms that are showing up in these differences, I have the partial with respect to z and then with respect to y, minus a partial with respect to y and then with respect to z. Same two variables, just in different orders. The assumption that we have continuous second order partial derivatives is what's going to allow us to use Clairaut's theorem and switch the order of differentiation here. What that means is that these two terms are equal in each set of parentheses, making each component function 0. That means that we're looking at the 0 vector field. So that proves this theorem. The curl of our gradient is the 0 vector. Okay, so how do you use this if we want to talk about a vector field being conservative? Well, here's an example. I want to show that this function here, this vector field, xy squared I minus xzk, is not conservative. If it is conservative, then its curl should be 0. I do want to point something out about this theorem before we jump into this example also. What this is saying is that if you're taking the curl of a conservative vector field, then you should get 0. What it does not say is that the curl of, if the curl of a vector field is 0, then this vector field is conservative. Okay, so it's if-then in one direction, but not necessarily the other. If we already know this is a conservative vector field, then its curl is the 0 vector. But knowing that the curl of a function is the 0 vector does not tell you that it's conservative, at least according to this theorem. That would be the converse of this theorem. We're going to show after this example that a version of the converse of this theorem actually does exist, but under a specific condition. So let's go ahead and do this example. If this is a conservative vector field, according to that theorem, its curl should be the 0 vector. So I'm going to try taking the curl of this. Curl of f is equal to del cross f, which is ijk up here, differential operators in my second row. Okay, and then my component functions. Xy squared is my I component. Notice my j component's not here. That means it's 0. My k component is negative xz. Okay, so let's start with my I component. Partial derivative of negative xz with respect to y is 0. Partial derivative of 0 with respect to z is 0. So I do have a 0 for my I component. Now moving on to the j. We know that the minus is just going to switch the order here. So I'm going to start by taking the partial derivative of xy squared with respect to z, which would be 0, minus the partial derivative of negative xz with respect to x. That would be negative z. So minus negative z, that's plus z. And that's my j. And then my k component, partial derivative of 0 with respect to x is the same thing as if it were with respect to anything, it's still 0. Partial derivative of this with respect to y is minus 2xy, and that's my k component. So I end up with this vector field, zj minus 2xyk. This is not the 0 vector. It's not the zero vector field. So that means that this function could not have been conservative. If it were, I would have gotten the 0 here, and I'm not getting that. Interesting criteria for showing that something is not conservative. But like we said, if the curl did come out to 0, at least according to that theorem, this would have been inconclusive. What we would need to show that it's conservative is some kind of converse of that theorem. And that's what we're going to talk about next. So if f is a vector field, and if it's defined on all of R3, and if its component functions have continuous partial derivatives, and the curl of f is equal to 0, then f is a conservative vector field. Really, the main criteria here that we need to be in place is that f is defined everywhere. It's defined in all of R3. It doesn't have any restrictions on its domain. So in those cases, if I were to evaluate the curl and get that this was equal to the 0 vector, then it would say conclusively this is a conservative vector field. Now we don't want to prove this theorem here because we need Stokes' theorem, which is going to come up in section 16.8. We have a little ways before we can prove that, but we'll talk about it then. Okay. Before moving on to divergence, which I'll probably do in the next video, let's talk about an interpretation for this term curl. From here forward, the more we get into vector calculus, the more we're going to look at things from the perspective of fluid dynamics. The concepts of calculus 3 and vector calculus in particular are applied in a number of areas, but the easiest applications to visualize, the easiest way to motivate some of the definitions and theorems that we come up with later on come from the concept of fluid dynamics, where we think of the vector field that we're working with as a fluid in motion. Okay, so air currents, water current, things like that. So how, in the perspective, of fluid dynamics, do we interpret curl? Well, we can't show this quite yet. Again, we need some theorems that come up later on down the line. But the idea of curl is that when you take the curl of some point in a vector field, remember the curl is in itself a vector field. So if you take the curl at a particular point, that's going to correspond to one of the vectors in that vector field. What this curl is a measure of is a tendency of the fluid in this vector field to rotate about the axis that curl vector points along. Okay, so if we interpret this vector as an axis, then the fluid may have a tendency to rotate about that axis. We can see that. I think your book makes an interesting little image for this, where it says, imagine a tiny little paddle wheel affixed to an axis that aligns with the curl. The curl is a measure of how quickly that paddle wheel will rotate on that axis. If the curl at a particular point is equal to 0, notice I'm not saying that the curl of the entire vector field is the 0 vector field, but if the curl of a vector field at a specific point is 0, then we say that f is irrotational at p. And if you think about why that would be the case, if the curl is 0, that means this vector here is the 0 vector, which means it has no magnitude, it's just a point. The interpretation is that the fluid in that vector field is not rotating in any way around some axis going through that point. Okay, it may be passing, well, we'll talk about interpretations a little bit later when we get into flux and stuff like that. Okay, so let's see, yeah, that's kind of an intro to curl. We're going to move on to divergence in the next video.